Okay, a quick review. We derived the Bernoulli equation in Chapter 3. It's one of the most basic equations in fluid mechanics. It has a number of assumptions about it that must be satisfied. They're listed here. Number 1 is a steady state equation. Number 2, the fluid is incompressible and inviscid. Inviscid means that the effects of viscosity of the fluid can be neglected. And finally, it applies along a streamline. And we worked an example problem last time from using the Bernoulli equation. And we're going to work a few more today. Okay, I've drawn one of the schematics for problem 324 on the board. 324, yeah. You've got problems in that area too, 336, 319. So it's somewhat similar. Let me read the problem statement from the textbook. A pitot-static tube. Now, we're going to talk about what that is in a few minutes, but for right now, this thing is called a pitot-static tube. Is used to measure the velocity of helium, well, it's not air, in a pipe. That's helium. The temperature and pressure are 40 Fahrenheit and 25 psia. Okay, a water manometer. That means there's water here shown by the diagonal line fluid water. Connected to the pitot-static tube indicates a reading of 2.3 inches. Okay, so we've got 2.3 inches. Determine the helium velocity, which is V in the pipe. Okay, so. All right, so as we're in Chapter 3, we know we're probably supposed to use Bernoulli equation, so it's not a big guessing game about the equation. The equation is going to be Bernoulli equation. Why? Because there's a velocity in the Bernoulli equation. There's the Bernoulli equation. What we said last time, there are 3 different variations of that Bernoulli equation. They're all the same, Bernoulli equation, but they're just 3 different forms. This was called the head form. Everything in here is in terms of meters or feet. This one is pounds per square foot, or kPa, possibly. This one, Poirot version. Okay, so we can use any one of the 3. I think I'm going to use this guy right here, the third one here. Yeah, okay, so first thing is pick one of the equations you want to use. Number 2 is you've got to show a point 1 and a point 2. Okay, I said last time, you typically select points 1 and 2 as, first of all, if you want to find something somewhere, that should be a point. The other thing is, if you know a lot of stuff somewhere, that should be a point. So I want to find something somewhere. I want to find velocity. So I'm going to say, I'm going to call this point 1. That's the velocity at that location. Now comes what? Another point where I know something. Well, I'll tell you what I'm going to do. I'm going to take this as point 2. Just in front. Now, let me describe what this is. This is an open-ended tube. Open-ended tube. Bent like this with a U. This is a U-tube manometer because it has the shape of a U-tube manometer with a different fluid in it. This is helium, a gas. This is water, a liquid. Okay, and then it's attached here. You drill a hole in the pipe and attach it right here. This one sticks down in the pipe and it points right directly towards the fluid coming toward it. Okay, now I'm going to write that Bernoulli equation from point 1 to point 2, P1 over gamma. plus V1 square over 2G plus Z1, now I do 0.2 okay. Why can I say that? Because these three terms are a constant. No matter where along the streamline you are, these three terms are the same constant. So whether I'm at 0.1 or 0.2 or in the middle here somewhere, those three values are the same constant. Okay. Now I start to make things simpler. Z is the elevation above some datum. I don't know, take a bottle of blackboard. Z1 from here up to here. Z2 from here up to here. Notice they're the same, it's horizontal. So Z1 equals Z2. Okay, here, here, gone. Now comes the little bit tougher part. At point 2, the velocity is 0. Point 2 is called a stagnation point. Point 2 is a stagnation point. V2 is 0. V2, gone. Why? Well, here it is. When I get to this point here, can the fluid flow up this way? No, look, there's water in there. If the fluid flowed in there, it would blow the water out. No, it doesn't. The fluid is static in that tube. The fluid is static in the tube. Which means if it's static, if it's not moving here, it's not moving here, it's not moving there at the entrance to the tube. That's my point 2. So the fluid at point 2 has 0 velocity. Here's my streamline, horizontal, 1 to 2. Here's my streamline. Okay, the equation now has reduced to something much, much simpler. P1 over, let's do the V1 squared. V1 squared over 2G is equal to P2 minus P1 over gamma. You got to do your bookkeeping correctly. There are 2 gammas, so you better differentiate those gammas. One's water in the manometer and one's helium in the pipe. Gamma W is water, gamma no subscript is what's in the pipe, helium. Okay, helium. Okay, so let's first of all, this is helium and we need gamma. Let's go ahead and solve this guy out here then. Our density, P over RT. Okay, and let's see what our P, well, we have to go through the pressure, 25 psi, isn't it? Yeah, 25. Did I write that down? Let's see. Oh, let's put it over here. T in the pipe and P in the pipe. Okay, he says, I'll read it again. The temperature and pressure of the helium is 40 degrees F, 25 psia. Okay. So 25 psia, 144, conversion factor gets it in pounds per square foot, divided by R for helium. We go to the inside front cover. Under liquids, or under gases, pardon me. Oh, not inside front cover, that's air. So let's go to the back of the book. If we can't find, if it's not water or air, go to the back of the book. Let's see where helium is. Oh, I know this. It is in the front. Let's double check that. I think it's in the front. Oh, it was in the front. Yeah, there it is. Yeah. Okay, helium. We have in English gas constant helium. There it is. 1.242. 1.242 10 to the 4. And T, don't forget T is absolute, absolute. 460 plus 40. Degrees are the units for helium in the back of the book. What pounds per slug degree are? And let's see, when I do that, I end up with density 5.80 10 to the minus 4. Slugs per cubic foot. Okay. There you have it. But always check your units. Always check your units, because that sometimes is what makes the big difference. Is you don't check the units. Always check the units to make sure it's going to be right. Okay, we have rho. We need gamma. So gamma equal rho g. Okay, got that. I can get that. I'll replace that with rho g up there. What's left? Well, there's another g right there. They're going to cancel out anyway. Okay, fine. I need P2 minus P1. Okay, now comes, this is chapter 3. Back to chapter 2. P2 minus P1, U-shaped manometer. Okay. Start at point 2, P2. What do? We go up. How far up to that black dot? Minus gamma helium times that distance. But don't forget what we said in chapter 2. If you've got a gas and a liquid in this manometer, pretty much you can neglect the density of the gas compared to the liquid. You can forget about it. So what we're going to say then is we're going to say the pressure at 2 in the helium right here, here, is the same as it is there. Okay, now I know the pressure here. Now what do? I go up. How far up? H. 2.3 minus gamma of water times H. That gets me the pressure right here at the helium water interface. Now, chapter 2, that's a static fluid in there. Everything's static. Nothing moves in that tube. That's the same pressure there in helium as it is there in helium. Okay, I'm there now. Now I go down to helium plus. Gamma helium times this distance. I don't care. I'm going to neglect it, because I know the density of helium is much, much less than the density of water. And what's it equal to then? That's equal to P1. So what is P2 minus P1? Okay, P2 minus P1 is then equal to gamma water times H. So put all that stuff back up here. V1 squared over 2G is equal to P2 minus P1 gamma water times H divided by gamma. Okay, and my gamma here is rho times G. G's cancel out. Gamma water is, we said what it was, 2.3 inches divided by 12. I'm sorry, H of water. 2.3 divided by 12. All the numbers are there, rho's up there, 2's down here, square root. When you're done, you get V1, the velocity of helium in the pipe, 203 feet per second. 203 feet per second. Okay, that's called, that. Okay, let's go back to here again. I'm going to do this. Okay, when we wrote this equation, this is in pressure terms. Pressure terms. Just a quick review. This is called the static pressure, P. This is called the dynamic pressure. This is called the hydrostatic pressure. And everything together is called the total pressure. Okay, here we go again. Static pressure, dynamic pressure, hydrostatic pressure, total pressure. So, at point 2, stagnation, by the way, these two guys here are called stagnation pressure. Okay, stagnation pressure. So how many pressures are there? 1, 2, 3, okay. The total 4. These two make 5. 5 different pressures. Know what the words mean. So if you get a problem that says the stagnation pressure is this, or the static pressure is this, you know what I'm giving you for a problem. Okay. Yep. Okay, go up here. This point right here is the stagnation pressure. This point right here is the static pressure. Okay, so this pressure cap here measures static pressure. This pressure here, stagnation pressure. Bring the fluid to rest. Stagnation, bring it to rest. Okay. Most people don't. When do they do this? When do they do this? To find the velocity at a point in a pipe or a duct. An HVAC duct, like the HVAC ducts in the room, or a big water pipe. If you want to find the pressure or the velocity somewhere, you can do this. Okay? Static pressure tap, stagnation pressure tap. But people, oh, by the way, did somebody lose a ruler here by my massive chair on this?
That was actually mine.
Okay, yeah. He found it for you. Thank you, Matt, later.
Thanks, man.
Here's a, this is a pitot-static tube. This is a pitot-static tube. You put that thing in a pipe like that. Okay, like that. In the front, there is a hole in the nose of the tube. That's a stagnation point. Like in front of your car, there's a stagnation point where the velocity comes to 0 near the grill. On a missile or an aircraft, there's a point in the front where the flow comes to 0 velocity. That's a stagnation point. I don't care if it's a bus, there's a point in the front where the velocity is 0. That's a stagnation point. Okay, that's a stagnation point. There it is mounted in there. This pressure tap up here measures the stagnation pressure. This side, a part of this side. That tap measures that. Now, there's also static pressure taps. They're hard to see, but they're around the circumference right here at my fingertip. There's little tiny holes drilled in there, about 8 of them. Around the tube, little tiny holes drilled, 8 of them. streamlines of the, if this is an ear, streamlines go like this, okay? So the holes are placed normal to the streamlines. That's how you measure static pressure. The holes you drill are drilled normal to the streamlines. That measures static pressure. Now, this is a tube within a tube. There's a big outside tube, and inside of here, there's a smaller tube. The inside tube carries the pressure from the nose. The outside tube carries the pressure from the static taps. This one, put it in a duct. This one, the high pressure goes over here. The low pressure goes over here. Put it on a U-tube manometer, and then measure that delta P. Measure delta P, put it up here, and find the velocity anywhere you want in the tube or the duct, like this. Put it anywhere you want. So these guys are used frequently. We have one set in the fluids hydraulics lab. They come in different sizes. There's a little one in different sizes. There's big ones and there's little ones. Okay. That's not the only way to measure velocity, but it's one that's used many times. Other things are called hot wire anemometers. There's one little turbine blade that spins, and you hold it outside in the wind. It'll tell you the wind speed. The little propeller blade spins with the wind, and you get the velocity that way. So yeah, that's just one way to get velocity. But it's a good example of a Bernoulli equation. Okay, so know how to do this calculation right here. That's important. So practice doing that. Why didn't I add 14.7? Because he told me it's absolute. That means I don't need to add 14.7. It's 25. That is absolute already. Okay. Now, let's take a look at 361. There are, in this chapter, there's a total of what we're looking at of 14 examples. That's one reason we chose this textbook, because there are so many worked examples in this textbook. So, between the problems I work in class, the problems worked out in that chapter, and the problems you do for homework, you'll have a library of probably 50 worked problems. 50 worked problems for the second exam. You know, and the more problems you see worked, the less you're liable to be surprised on an exam. The more problems you see worked, and especially worked yourself, you can look at problems worked out all day long and not too long on an exam. But if you go through them in great detail, then you'll be ready for an exam that way. Okay, so let's take the other one I want to work, 361. Okay, we'll put that, I think we'll put the sketch right here. 361, okay. Water is siphoned from a tank. This is called a siphon. That's a way to measure velocity over there. Now we're going to do a siphon. Okay, so here's the water tank. Okay, the siphon's at the bottom, comes out, goes over, down, comes up this way. Okay, that's open there. Okay, let's put some dimensions on this. I think that's 8 feet. 8 and 3. So this from here to here is 8 feet. And this distance from the free surface down here is 3 feet. Okay. The purpose of a siphon is to drain a tank. without drilling a hole in it. Okay, so you put a tube in there and you take it out the top, put it down here. And do you need a pump? That's not supposed to. It does it all by itself. Wow, isn't that neat? Yeah, it does it all by itself. Okay, so let's keep reading. Determine the flow rate from the tank. So find. Now, there are different things you can find. Number one, somebody can ask you to find V. V stands for velocity. We just did it over here. And you might know this stuff from physics fine. Maybe you've had thermal, maybe not. If you have, this is review, but that's okay. V is velocity. Okay. Now comes a flow rate. Okay, this HVAC duct in here. You think those guys, when they analyze those HVAC ducts, say the flow rate in there is 50 gallons of air per minute? Are you kidding me? 50 gallons of air per minute? No, you know the language they speak? CFM. Or maybe liters per second. No, that's called volumetric flow rate. So number 2, Q, volumetric flow rate. Okay, to calculate it, you take the velocity times an area. Velocity, feet per second. Area, square feet. Q, cubic feet per second, or cubic feet per minute, CFM. That's called volumetric flow rate. Now, if we multiply that by the density, we get mass flow rate. That's rho AV, or rho times Q. Pounds mass per second, kilograms per hour, whatever. Oil pipeline carries so many pounds per hour. A steam power plant, the line going to the turbine carries so many pounds per hour of steam. They don't say it carries so many CFM. They don't give you the velocity, they give you the mass flow rate in these power plants or chemical plants. If it's HVAC work, they give you the volumetric flow rate, Q. And once in a while, if you're analyzing flow in a river or something, you might want to know the velocity. You want to find V. So there's various times you want to find each of these 3 things. Depends on who you work for and what your job is. Okay, now, this particular job says, he wasn't very specific, he said find the flow rate. He means to find Q. Okay, I would be more specific on the exam. I would say find the volumetric flow rate for the mass flow rate. But there they are, all 3 of them. Okay, and then he says, and also find the pressure at points 1, 2, and 3. 1, 2, and 3, okay. Now, I'll give you point 1, 2, 3 soon. Okay, so. Anybody ever siphon anything out of a container? What do you do first? Like how do you do it?
Taking a hose and like a water trough.
Okay.
Fill the hose up with the water completely.
The hole completely, right? That's the key, right?
Yeah.
Get everything underwater. Get water in there first, right?
Yeah.
Then what do you do?
And then you cap off the ends so it doesn't lose the water.
Put your finger on one end, then raise it out.
And raise it out, and then put it underneath the
The level of the reservoir.
Water,
Perfect. Okay, you're an expert at it, I can see that. Gasoline, I hope not. Okay, right. Excellent steps. 1, 2, 3. You're exactly right. So you know, you just don't put the tube in there and say water's going to come out of here. You know, it's not going to come out. No, put it all underneath there. Get it full of water. Put your finger over it. Then raise it out of here and put it down below this, and now take your finger off. Voila, fluid comes out. Okay, good, good. Okay, we're in chapter 3. We must have to use Bernoulli's, obviously. Okay. Is it steady state? Not exactly. Which is probably a good point. Let me just check this. 361. 361. Okay. Yeah, okay. Let me check something else here. He doesn't always say this, and I think the next problem I'm going to work, he says it. Let me just double check this and see. Problem, okay, yeah, problem 380. Let me check problem 380. I'm going to read problem 380 to you. This is a problem with the tank and a hole in the bottom, water coming out. He says, the tank is large. So what? The tank is large. They don't always say that. If they don't say it, assume it in chapter 3. He won't always say it. Sometimes he will. Problem 380, he says the tank is large. This problem just says the tank. Okay. Why is it important to say the tank is large? Because if I want to use Bernoulli's, it's got to be steady state. And if I put this thing in a coffee cup, it'll drain in a few seconds. Well, that level's going to go down fast. Illegal. Illegal. That water level should stay the same. If this is big enough and that's small enough, it'll stay the same, relatively speaking. Okay, so that's why we satisfy that guy. If you don't see the word large tank in a problem in chapter 3, you assume it's a large tank. Otherwise, if it's not steady state, you can't use Bernoulli. Number 2, incompressible. Yeah, it's water. Inviscid. Okay, we have to neglect friction. Is that easy to do? Yes and no. It's not bad here, but when we get in this tube, there's going to be some viscous effects. There's going to be maybe a pressure drop due to viscosity in that tube, but in this chapter, we're going to neglect it. Come back in 3 weeks and we'll talk about how we account for viscosity. Okay, so yeah, we know there's some viscous effects in here, but we're going to ignore it for right now. Okay. Along a streamline. Well, not yet, but it's going to be. Okay, here we go again. I'm going to have to start somewhere. Okay, so I'm going to call that point 1. Now I'll tell you where he put points 2, 1, 2, and 3. He put, I don't know if I have to change mine here. He called that, I don't like that, point 0. Okay, so I'm going to call that point 1. So it's going to be point 2, 3, and 4. I've changed the problem statement because he puts point 0 up there. I don't like doing that. So that's point 1. Here's point 2. Here's point 3. Oh, here's point 3, pardon. There's point 3. There's point 4. There's point 5. Okay. Now, I know with the siphon, the water's going to come out of here. That's a siphon's purpose in life. Water comes out of here. I know I want to find that velocity, v5, because I know Q is V times A. What A? The area of that pipe, right there my fingertip is. Okay, so I got to find V5. Okay, fine. Over there I had to find V1. What I do? Bernoulli's. Over here, what do I do? Bernoulli's. Okay, from what? 1 to 2. Over here, 1 to 2. What's my equation? There it is. Okay. Here's my streamline. Right there. Okay, let's write the equation down. There it is. I'm sorry, there it is right there. So let's put a check mark by what we know. P1 up here. Again, this typically means atmosphere, so P0 gauge. But I know it. V, he said a large tank. Therefore, the velocity on the free surface is assumed to be 0. Got it. Z1. Got it. Z2. Got it. V2. I don't know what the velocity is in there. P2. I don't know what the pressure is just at the pipe inlet. Just at the pipe inlet. This is not fluid statics. It's not gamma times this because the fluid is moving at point 2. So it's not chapter 2, fluid statics. This is chapter 3. I've got a problem. I've got one equation, 2 unknowns. Nope, that didn't work. Try again. 1 to 3. Do I know the velocity at 3? No. The pressure at 3? No. 4. Do I know the velocity at 4? No. Do I know the pressure at 4? No. Try again. Do I know the velocity at 5? No. Do I know, here it comes, the pressure at 5? Ah, what at X at 2? Atmosphere. Oh yeah. One equation, one unknown. From where to where? 1 to 5. Okay, so P1 over gamma, V1 squared over 2G, Z1 equal P5, pardon me, P5 over gamma, V5 squared over 2G plus Z5. Okay, P1, 0, V1, 0. Exit to atmosphere at 5, P5, 0. Okay, there it is. V5 squared equal 2G Z1 minus Z5. Okay, let's see if I found that one. Yeah, there's 13.9 feet per second. Take the square root out. Let's just make that right. Okay. Now let's try the next step. Oh wait, I didn't get the Q, so I'll get Q. Okay, 2-inch diameter hose. 2-inch diameter hose. Given.
When we're doing Z1 minus Z5, is that just going to be positive 3? Because if you just do 0...
yeah, I'm calling
the datum at the bottom?
Okay. Right there, right by
That
here.
makes more sense.
Take a convenient spot, did you know? Yeah. Okay, there's answer part A. Now I'm going to do part B. Okay, P2, there's 2. Now I can go back to 2. So start again. Oh, there we are. Here it is. 0, 0, Z1, yeah, 8. P2, unknown, find it. Okay. Steady state, conservation of mass. Same diameter pipe. What comes in here goes out here with the same velocity. Steady state. I think it's pretty straightforward, but okay. Mass that comes in at 2 in the pipe equal mass that goes out at 5. Rho A, B. Is the density the same at 2 and 5? Yes, it's water. Is A the same at 2 and 5? Yes, it's a constant area pipe. Therefore, the rho and the A cancel out, which concludes then that V2 equal V5. Okay. Z2 we call 0. Put the numbers in. You know gamma. So the pressure at 2, 312 pounds per square foot. Gauge your absolute. To answer that, you say, well, what's this pressure 1, 0? Gauge your absolute. And the answer is gauge. So if P1 is gauge, P5 is gauge. Okay. 1 to 3. Well, this is interesting. Looks like Z1 equals Z3. Ah, that's right. Z1, Z3. P1, 0. V1, 0. Oh, okay. So, P3 and P3. Oh, minus V3 squared over 2G. Okay, here it comes again. Steady state, constant diameter, incompressible, V2 equal V3 equal V4 equal V5. So it's the same thing, V5. And let's see what pressure that was. P3, yeah, okay, minus 187. Okay. Let's stick the last one right here, maybe. Obviously 1 to 4. P1 over gamma plus V1 squared over 2G. Now, if you want, you could write it from 2 to 3 Bernoulli. Write from 2 to 4 to Bernoulli. Write from 2 to 5 to Bernoulli. So, you know, there's lots of choices. Some are easier than others. In this case, it doesn't matter too much because these guys are all straightforward. P4. P1, 0. V1, 0. Oh, I didn't quite have there. I'm going to, I'm going to call this H just for fun. This is not part of the problem in the textbook, but I'm adding something to it. Okay, so we're going from 1 to 4. So I'm going to call Z1 0. See, I can change my datum anytime I want, as long as I use the same data in that datum in that equation. So I'm going to call my datum here now. So Z1 is 0. If I want to, I'll put my datum up here. Okay, what is Z4? 0. What is Z3? Minus H. What is Z2? Minus H plus 8. You can put your datum anywhere you want. Okay. Z4 is H. P4 don't know it. V4, I know it. So P4 equal gamma times minus V5 squared over 2G minus H. Okay. Now, notice that the pressure is getting lower and lower. Matter of fact, it's negative here. Okay? If we raise this point 4 up high enough, the pressure is going to get low enough so that the water will start to vaporize, and we'll get vapor bubbles in there. And then it won't work anymore. The siphon won't work anymore. And the pressure at which it starts to vaporize, you go to the inside front cover, under water. Vapor pressure is listed right there. Vapor pressure inside front cover. So if I want to know the height at which this won't work anymore, the siphon won't work anymore, I go to the inside front cover. I get the vapor pressure of water at a certain temperature. I put that pressure in here. I know V5. I know gamma. I know G. Find H. Yeah, up here somewhere. High enough up here, the siphon won't work anymore. It'll stop working. Yeah.
What does it mean when you have a negative pressure inside a tube?
Okay. If I've got water, let's say your household pipe. I hope not. But if the pipes are in your ceiling and they get a pinhole leak in it, will water come out of there, or will air go into that pipe, you think?
Air will go in. Or
Oh no. Many people have flooded their house because their pipes in their roof are old, in their attic are old with corrosion, and they get a pinhole leak in it. Call the insurance company. My rug's full of water. My drywall's wet. No, water will come squirt. That pressure is about 60 or 50 psi. Oh, it'll come out of there. Now, sometimes in a pump that draws water in, if there's a leak on the inner side, then air might be sucked in because the pressure's below atmospheric. The pressure's below atmospheric. So there's sometimes the fluid comes out, other times the gas comes in. So that's negative pressure. What's the absolute pressure? Well, you know, this guy here plus 14.7. Okay. The pressures in here, I'll read it to you. The pressures in here, vapor pressures, it says right there in the column, absolute, those pressures are absolute in there. So, you know, watch out. That's gauge, okay? So you have to watch out your units, absolute or gauge. Yeah, so yeah, that's what happens. The pressure gets so low that the liquid water, it gets vapor bubbles in it, and then it won't work anymore. It's somewhat similar to your car, your gasoline line. Ever hear about vapor lock? I thought gasoline's a liquid. Where'd the vapor come from in my gas line? Where'd it come from, you think? How do I turn the vapor?
Low pressure.
What? Either low pressure or a high temperature. High temperature? Oh yeah, oh yeah. It can turn gasoline into vapor. Vapor lock, no more gasoline's pumped to the engine, engine stops. Up here, you get high enough, guess what happens? No more pumping action, water stops flowing out. Anyway, that's a sidelight, but just so you know, we've taken all these various points. Free surface, inlet to pipe, exit to pipe, same elevation. Why is the pressure different here? And it is, of course, because this is on the free surface, this is inside the pipe. That's what that 0.3 is meant to show you. They have the same elevation, but the pressures in those two are different. Compare P10 to P3. If we got P3 there, right there. Minus 187, they're different. Okay, what if I put my 0.1 here? Or what if I put my 0.1 there? Does it matter where on the free surface I put my point? No, because they all are going to go down there like that. So it doesn't matter where you put your point. You say, I don't know if the water molecule goes down like that. You know, maybe the water molecule, I don't know, maybe it does this to get down there. I say, I don't care. Just draw the line, okay? The main thing is along a streamline. Where's the streamline? Oh, I think it looks like that, but maybe like that. Does it matter? No. No. Okay? So don't worry about where you put 0.1 on the free surface. Okay. Let's see, anything else that we need to discuss? I don't think so right now. Anything else? Okay, siphon. Let's take a look at another one. And if you get confused on a problem or an exam, what do? You look at that picture and you try and figure out where you know the most stuff and what you want to find. And that, I tried 1 to 2, that didn't give me the velocity. 1 to 3, no. 1 to 4, no. 1 to 5, yes. You keep trying. Sometimes you don't automatically see it that way. Okay. 381. Water flows steadily downward in the pipe shown. Okay, right this way. Static pressure tap on the left, on the right part. Static pressure tap on the left, up here. Okay, let's see what we know. Okay. This is oil. Specific gravity 0.7. This is water, so gamma water. Okay, let's see, 1.5 meters up here. And from here to here, 2 meters. think that's all we need here. Determine the flow rate. Okay, that's, you know, the flow rate, V times A. Number one, gotta find V. How? Bernoulli. Okay. I think it's pretty apparent where you're going to put points 1 and 2. I mean, you can't be too random. I say, I don't know, I like that point. That's neat. And you know what? I think I'll put point 1 here at the point 2 at the exit. No, first of all, that's not an exit. That's not an exit to air. That doesn't come from air. When I draw a pipe like that, I mean the pipe goes on, up and down. How far up and down? I don't know, but a long way. So that's not an exit. If it's an exit, I would put down here P atmosphere and put up here P atmosphere. But that's not an exit. That's a continuous pipe. Okay, so you don't want to randomly put point 1 and point 2, something like that. You say, where is this manometer attached? Oh, this point right here. And, oh, this point right here. So I'm going to call this 1, I'm going to call that 2. It's very similar to statics. If you don't choose a good free body diagram, you're going to stumble around for a while until you find it. Likewise here, if you don't choose points 1 and points 2, good. You're going to stumble around until you finally get the answer, because it's going to take you a while. So, choosing points 1 and 2 is very important in this. Okay, here we go again. It's over there. Okay, gotta find the velocity. There's 2 unknown velocities there, V1 and V2. Matter of fact, if we look at that, we might say, you know what? I'm gonna find P1. This goes back to our chapter 2, where we had a pipe like this with there's a velocity here, and we attached this glass tube up to here. Okay, this is water, for instance, and that pressure at the pipe center line was gamma times H. Gamma times H. By the way, is the water moving in the glass tube? Of course not. Is the water moving in the pipe? Of course it is. That's fluid statics. This is where fluid moves. So, what's P1? Drill a hole in the side of the pipe, put a glass tube on it. Water goes up 1.5 meters. P1 is gamma, 1.5 gamma. And we're going to call that gamma water, so we get our gamma straight again. There's water and oil in this problem. Okay, now we'll get P2. Okay, P2. Okay, it's a manometer. Water here. Okay, go up here, 2 times gamma water. Plus, now this is gamma of oil, 1.5 gamma oil, So P2 minus P1 is equal to 2 gamma water minus 1.5 gamma water plus 1.5 gamma oil. P2. Oh, this guy, yeah. D1. .5 gamma water plus 1.5 gamma oil. Divided by gamma water. P2 minus P1 divided by gamma water equal 0.5 gamma water divided by gamma water plus 1.5 gamma oil over gamma water equals 0.5 specific gravity of water plus 1.5 specific gravity of oil. Specific gravity of water, 1. Specific gravity of oil, he told me, 0.7. So that's the nice way to lay it out, step by step. Don't take shortcuts. Okay, so let's go ahead then and find out, okay, so now I've got those guys taken care of down there. Okay, so Z1, I'll call 2 my dad. Z2 is 0. My choice. Z1, 2 meters. Okay, everything's known except 2 things. I don't know V1, I don't know V2. 1 equation, 2 unknowns, I'm stuck, can't solve it. Not yet. Okay, can't solve it. So I need another equation. That's 1 equation, 2 unknowns. I can't write any more Bernoullis. There's no more points on there to write other Bernoulli equations. It won't help me to find another Bernoulli equation. There's no more logical points to choose. Okay, so Bernoulli's out. Okay, here we go. When you get stuck, think about this guy. Conservation of mass. Do you think the mass flow rate at 1 is the same as 2? Of course it is. It's incompressible, steady state. Is mass being stored in there? No. Is it incompressible? Sure, it's water. Question here.
Why is it not useful to add another Bernoulli?
Like from where to where? Give me an idea where.
Like above the oil at the top of the surface of
Okay.
the top of the surface of the oil.
There. Is the fluid oil moving there?
No.
Then don't write Bernoullis.
Oh, okay.
Bernoullis is meant to be written where along what? Along what? A streamline. And along a streamline, what happens? There's a velocity. So you don't want to write it from 2 up to the oil. That's fluid statics. That's chapter 2. We're in chapter 3. Okay, so let's rewrite this. All right, now, missing link, conservation of mass. We're going to do official conservation of mass in about 2 weeks, but for right now, this is just kind of a low-level conservation of mass. The simplistic one, the one we pretty much all believe. You've got a garden hose. 5 gallons per minute come out the end with the nozzle. Do you think 5 gallons per minute comes in from your house water supply? Of course. You're not going to, water's not being, created out of nothing. So yeah, you'd believe that. Okay. M dot 1 then must equal M dot 2. What's M dot? I wrote it down. Rho 1 A1 B1 equal rho 2 A2 B2. What's the fluid? Water. Is it incompressible? Yeah, we assume it is. What does that mean? The densities are the same. Rho 1 equal rho 2. Here comes the catcher now. Are the areas the same? No, no. Pi d1 squared divided by 4. Pi d2 squared over 4. Cancel out the pi's, cancel out the 4's. Which is the, let's write it in terms of 1, yeah. So B2 then is equal to d1 over d2 quantity squared times v1. So wherever you see in that equation a v2, replace it with that. So replace that v2 with d1 over d2 times v1. Now what are you left with? One equation, one unknown. What's the unknown? v1. So from here, solve for v1. So you gotta get an answer on that one.
That d1 over d2 is squared, right?
Oh, yeah, thanks. Good. No, I didn't get an answer. I want to set the equations up. Try Bernoulli's, fine, it's true. You're stuck, you can't get v1 or v2. If you're stuck, look at conservation of mass, good. Now there are two equations with two unknowns, solve them for v1. Once you get v1, then q equal v1a1. Okay, now, we're going to come back with one more problem a week from today, but I just want to mention from Monday now. From Monday, we're going to review for the midterm. I'm going to go over some problems that I saw people have difficulty with on homework or office hour questions. I'll try and address those on Monday. If you have any specific problems you want me to look at Monday, homework or whatever, example of the textbook, email me and say, Professor Biddle, would you please look at problem 285? I have questions about it. And if I can, if there's enough time, we'll do it. I'll do my stuff first, and then time left over, I'll look at the stuff you want me to look at and go over in class on special time. Okay, good stopping point. So we'll see you next Monday.